Let's talk about DC motors this time. DC motor is an application of the Lorentz force and forces between wires and Ampere's law as well. So we're effectively putting all the things that we've talked about before together. So let's consider a loop. This is the square wire, and let's put a current through it. And we sandwich that loop between magnets. Now if you look at the top segment of the loop, the current is running out of the page, magnetic field is acting to the right, and if you use your right hand rule with the thumb pointing in the direction of the current, index finger in the direction of the magnetic field, and the middle finger will then point towards the direction of the force. The force will be acting upward. And then the bottom segment will have force acting downward. And if this is the case, then if you do that to a sheet or a loop, then this loop will rotate. And of course, after some time, this bottom segment will be up here. And what that would mean is that the force will now be acting oppositely. However, notice this little gap here. When the bottom segment rolls around, the current will switch direction all of a sudden because of this little gap here. And the loop, after half a rotation, looks identical to the current position. And so the force will still act to the top here and towards the bottom down in the bottom segment. And this loop will continually rotate. This is just a DC motor. Now this is a nice application of electrical circuit to do some work. And of course you can think of many examples of DC motor. Now what's actually quite amazing is that DC motor works just as well backwards. So suppose instead of having a battery, so we have a battery here for a DC motor to rotate. Instead of having a battery, we put a resistor here. Of course, this loop will not rotate at that point, but what we can do is we can hand crank the loop. We can simply take arm and then rotate this loop. And doing so, rotating this loop in the magnetic field will generate current in the loop, and that current will then be dissipated by this resistor, and we can measure that, and this will be an AC current. So the question is, where does this come from? So Michael Faraday did a few experiments in the 1830s. And here are some of these experiments. Now this is a modern depiction of these experiments, so some of the tools you might have had not access to. So let's consider having a voltmeter, which is an object that measures voltage difference across two leads. And we'll take a wire and we'll coil it around, kind of like a solenoid that we've encountered. And we're going to stick a magnet into it. And what Faraday noticed is that when this is done, the needle on the voltmeter jumps. So it'll jump either to the negative or to the positive. It'll jump back and forth. And if you leave the magnet in there, then nothing happens, right? So it's only when you insert the magnet and when you pull the magnet out, only then the voltage changes. You need not actually put the magnet in there. You simply need to have magnetic field lines going through it. And this is something you can determine by doing another experiment by taking this horseshoe-shaped magnet, by placing it as is shown in the figure down here, and then moving it laterally back and forth. And what that will do is it will put magnetic field lines inside the loop and outside the loop. Now remember what happens when we have a current running through a solenoid. We have magnetic field lines. Now, what's interesting about that is that we're doing the opposite of that. We're putting magnetic field lines into a loop where there is no battery, so there is no current. However, as these magnetic field lines go in and out of the solenoid, they generate a current. And then finally, we can do another set of experiments where we set up a circuit on the left hand side with a battery and a switch, and we connect the wire, which has some insulating exterior. So in other words, it's got some plastic on the outside, and it's connected as a solenoid onto an iron ring. And on the other side, we have also a solenoid connected to an iron ring and connected to a voltmeter. Now this voltmeter needle will deflect every time we open and close that switch. Now this is maybe not so surprising for us, but this must have been fascinating for somebody like Faraday, who was now experimentally making invisible forces do things at a distance. So how do we make sense of this? So let's bring it back to Lorentz force. So Lorentz force talked about forces acting on a charged particle when it moves through magnetic field. So in the first figure here, let's consider moving a metal block through a magnetic field. Now remember, metal is something that has a bunch of charges that are free to move around. Now if the magnetic field is going into the page and the velocity of the block is to the right, then the force on a positive charge will be to the top. And in fact, what will happen is that if this metal is moving through this, then positive charges will move to the top. Alternatively, electrons will move to the bottom of the block. Now, if we're sitting on the block, that looks like an electric field going from top to the bottom. In other words, we've generated a voltage across this block, and electrons are moving to the bottom of the block while there is absence of electrons at the top of the block. And as the metal block continues to move, the next positive charge will be forced up until there is an equilibrium that's reached. And that equilibrium is reached with a bunch of positive charges on the top, or excess of electrons, and a bunch of electrons or net negative charge at the bottom. And that looks a whole lot like battery. Now, what's nice is that the force on these electrons is nothing more than the charge Q times the speed V times B. Since the magnetic field and the velocity vector are acting perpendicularly, the cross product simply becomes the product of their magnitudes. But if we divide the force on the left hand side by the charge, we simply get electric field. And we wind up with the electric field is equal to the speed times the magnetic field. So we can think of this difference in charges at the top and the bottom as a potential. And this is exactly how a battery works. And battery is constructing potential chemically. Here we have mechanical methods of constructing a potential on a block, but battery is doing it chemically. And both of these things are historically called electromotive force, although we no longer use that term and we just call it EMF. The reason for that is not really a force. It has the units of a potential. Now, based on these experiments, we can make the following conclusion. And this is known as Faraday's law. That electromotive force, the ability to create a potential in an object between top and bottom, is equal to the time derivative of the magnetic flux with a negative sign. And the negative sign turns out to be somewhat important. So let's talk about what magnetic flux is in a second. So let's consider a loop seen from the side and a bunch of magnetic lines going through it. And if we were to rotate that and look at it from the front end, we'd see these magnetic field lines coming at us. So those are depicted as dots. And so the magnetic field line, the magnetic flux is nothing more than the product of the magnetic field times the area. And area in this case is just the length and the width multiplied, A times B. But now if the loop was tilted, then of course our area vector would be pointing up, as was the case in electric flux. And so we'll have A times B times cosine of theta, theta being the angle between magnetic field lines which are pointing horizontally and the area vector which is pointing normal to the loop. And of course, if the loop becomes perfectly horizontal, then no magnetic field lines are actually going through the loop and the effective area becomes 0. So here's another case. We have magnetic field going up and we have a little loop with which is at an angle, and so the area vector is normal to the surface of that loop. And the way we compute that is we break up the magnetic field vector into its components perpendicular and parallel to the A vector, and then multiply that through to get that the flux through this loop is going to be the area of the loop times the magnitude of the magnetic field times cosine of theta. And this is magnetic flux. It's just like the electric flux, except now instead of electric field, we're considering magnetic field. So let's consider magnetic flux through a non-uniform magnetic field. So far we've encountered a situation where the electric field or the magnetic field is uniform. But in this example, it's going to be non-uniform. And this is depicted by the fact that the magnetic field lines are separated out. So where we have high density of dots, we have stronger magnetic field, and where we have low density of dots, we have weaker magnetic field. And we're considering an area with a height of b and some dA or some width that we're going to call dx. And so our magnetic flux for a differential element is going to be b times dA, and dA is little b times dx. And we're going to integrate over that. Now, the magnetic field in our case is given by a wire with a current running through it. This is depicted in red here. And so this is the source for the non-uniform magnetic field. Remember, when the current is generating magnetic field, it drops off as 1 over the distance. So we have the magnetic field going as mu naught I, which is the current, divided by 2 pi times x. And our differential area element is b, which is the height of the loop, times differential length element dx. We can do this integral. And integral of 1 over x is just a log of x, and then we plug in the limits. We start our loop at distance c away from the wire, and then we end the loop at distance c plus a away from the wire. And so we've computed the magnetic flux going through that loop. Now let's consider the case where we have current induced by magnetic flux. So what we're going to do is we're going to set up a circuit. I'm going to set up a wire in a U shape. So this is the U shape. I'll scan my face through it. And then we're going to put a bar here that's going to close the circuit. And we're going to move that bar to the left, to the right. And moving that bar is going to generate a magnetic, will generate a time-dependent magnetic flux. So let's talk about how the magnetic flux changes as a function of time. So in this case, the magnetic field is uniform and it's going into the page. So our magnetic flux looks like, or the change in magnetic flux looks like the magnetic field times the change in area as the bar moves from here to here. And let's say the bar is moving with velocity v. So it moves a distance of v times delta t in some time delta t. And that gives us our change in area. So the area that we get that changes in time delta t is just speed at which the bar moves, which is given as v, and times the length of the bar times delta t. And so the time derivative of the magnetic flux will be just the change of magnetic flux divided by delta t. And the delta t goes away and we wind up with a nice simple equation, which is the speed at which the bar is moving, the length of the bar, and the magnetic field inside. But remember that the EMF is also equal to this quantity, and so we wind up with this equation that the change in magnetic flux is equal to the EMF. And that's in fact Faraday's law. So now by having a magnetic field, we can make a simple generator. What we can do is move the bar, so we can put up a wire that looks like this in a U shape, put a metal bar and move it back and forth. And as we move the bar to the right, positive charges will go to the top of the bar and negative charges will go to the bottom of the bar, and that bar then looks like a battery. And therefore it will generate a current going from top to the bottom, going through the yellow wire, the loop. And we can of course move it back and forth, and we'll have alternating current that will oscillate sinusoidally. Now where does this energy actually go? Well, we're taking mechanical energy, so we're moving the bar back and forth, we're taking mechanical energy, and we're generating current. Now if we were to set up a resistor somewhere on here, say a light bulb, an old-fashioned light bulb which is resistive, then that current will run through that resistive light bulb and it will light it up. And so the mechanical energy will become into electrical energy, and then it'll become a radiative energy. And so we've converted energy from mechanical to radiative. Energy is conserved. Now there are a few problems that we can do about this, and we'll go through them in some videos and in the workshop in the next couple of weeks. Let me summarize the main ideas. That suppose we move a loop in or out of a magnetic region with a magnetic field, then the flux inside the loop, as it changes in time, will induce a current and will induce an electric field. Now there's one more thing to remember, that the induced current will always have, will always resist the change of flux. So it will induce current in the opposite direction so that the magnetic flux is not changing. And the main reason for that is, if you look at Faraday's law, it says that the EMF is equal to negative of d phi dt, the time derivative of magnetic field. So if the time derivative of the magnetic field is increasing, then the electric field is increasing in the opposite direction. And this is known as Lenz's law.